OCR Chemistry A, Atomic Structure, Isotopes and Relative Mass. Getting the most from Chemistry Explained means taking notes and completing tasks on paper or on a tablet, controlling the pace at which the lesson proceeds. Particularly when prompted, pause the lesson, complete the task, thinking it through, taking your time. When you're ready, return to the lesson and correct your work before proceeding. So let's start with a quick recap on the Bohr atomic model, which is the model that you most probably used at GCSE or pre-A level. This is the model in which we have a nucleus in which we find the protons, which are positively charged with a mass of 1, and the neutrons with no electrical charge but also a mass of 1. Those are found in the nucleus, may be referred to as the nucleons, but the nucleus, despite having the vast majority of the mass of the atom, is tiny compared to the rest of the atom. The third subatomic particle, so protons, neutrons, electrons are subatomic particles, is found in the surrounding space. Those are the electrons, which have negative electrical charge and negligible mass. You may have referred to them as being found in the electron shells surrounding the nucleus. Two numbers we need to know about are the atomic number, which is the numbers of protons, and the mass number. So each atom has an atomic number and a mass number. The mass number is the number of protons plus the numbers of neutrons. So in other words, it's the number of particles in the nucleus, so it's the mass of the nucleons. So the mass number is protons plus neutrons. We can also tell the electron number in a neutral atom, meaning the numbers of negative electrons is matched by the number of positive protons. We can also tell the numbers of electrons because those in a neutral atom must be the same as the number of protons. So let's remind ourselves what we can find out about the numbers of protons, neutrons and electrons in an atom from the atomic number as I've written it, and the mass number for any particular type of atom, any particular element. Well, we can deduce from those two numbers that the numbers of protons is 3. How does that come about? Well, of course, the numbers of protons is simply the atomic number. The numbers of electrons is the same as the numbers of protons, so that is also 3. And the numbers of neutrons, well, that's the difference. 7, take away the 3 protons, leaves you with 4 neutrons. So we get ourselves 4 neutrons. That's the difference between the atomic number and the mass number. We also need to know how to get the numbers of protons, neutrons and electrons in an ion. So let's look at the lithium ion, which is 1+, which means it has lost 1 electron. So the numbers of protons is still 3 because the atomic number has not changed. However, by being positively charged, it means it has 1 more proton than electron. So the numbers of electrons is now 2. So it's a 1+ charge because we've got 3 protons and only 2 electrons. So 3 positives and 2 negatives, overall 1 positive. The numbers of neutrons remains unchanged. That will still be 7 minus 3 equal to 4. Okay, so here are a few problems. Here's an element, mass number, atomic number. How many protons, electrons and neutrons? Similarly for aluminium, please note the third, fourth and fifth columns contain ions. So for each particle, can you write down the numbers of protons, electrons and neutrons? Take your time, pause the lesson, come back when you are ready. Okay, so here are the figures for the atoms. Fluorine, atomic number 9, so therefore 9 protons. The numbers of electrons are the same as the numbers of protons in a neutral atom. The difference between 9 and 19 is the number of neutrons. We add 9 protons and 10 neutrons to make 19. Looking at aluminium, 13 protons, the atomic number is 13, which means we've got 13 electrons, and 13 plus 14 makes 27. So let's discuss the fluoride ion, F minus, atomic number 9, so 9 protons, which would indicate in an atom 9 electrons, but we are carrying an additional negative charge, so there are 10 electrons, one more than there are protons. The numbers of neutrons, the difference between the mass number and the atomic number as usual. Now looking at the aluminium ion, the 3 plus ion, atomic number indicates 13 protons, but we have 3 more protons than we have electrons. The 3 plus charge means we have 3 more protons than electrons, 3 more positive protons than negative electrons. So we only have 10 electrons. The difference between the atomic and the mass number is 14. We're moving on to the oxide ion, 2 minus. Here we are carrying additional electrons, so the atomic number 8 means 8 protons. 8 plus 2 additional electrons makes 10 for the numbers of electrons, and the difference between 8 and 16 is 8 for the number of neutrons. So we're going to move on to the idea of isotopes. So I wonder if you just pause and think for a moment, tell yourself what an isotope is. Okay, so now it's my turn. Atoms of the same element with different numbers of neutrons. So different numbers of neutrons. So atoms of the same element means same numbers of protons, same atomic number, but different numbers of neutrons. So what does that mean in terms of atomic number and mass number? Write down the definition of isotope in terms of atomic number and mass number. Pause, return to check against my answer. Okay, so here's my thoughts. So isotopes are atoms that have the same atomic number but a different mass number. So they've got the same numbers of protons but a different number of neutrons. So same atomic number, different mass number. So let's look at some examples. Carbon-12 and carbon-14. You may have heard of those, the carbon-14 isotope in connection with archaeology. Could you write down the numbers of protons and neutrons in those two isotopes? Okay, I'm going to write down my version. So the atomic number tells us there's 6 protons, and the difference between 6 and 12 is 6 neutrons. So 6 and 6 makes 12. The atomic number has not changed. It's the same atomic number, but the mass number is different. So if they got 8 neutrons. So just a few problems to confirm to yourselves that you're fluent in all of this. We've got 3 isotopes of lead and 2 of hydrogen could you fill in the protons, electrons and neutrons for those 5 isotopes? Pause the lesson, complete that task, come back to check your answers. Okay, so as you can see, for lead, the atomic number is 82, which means the numbers of electrons is also 82, so protons and electrons are the same, and the difference between 82 and 204 is 122 neutrons. The atomic number does not change, it's still 82, which means the electrons is 82, but we've got 124 neutrons, and for lead 208, 82, 82, 126, of course. And now for hydrogen, atomic number of 1, so we've got 1 proton, 1 electron. Because the mass number is also 1, we don't have any neutrons. 1 plus 0 equals 1. However, we have an isotope of hydrogen, a very important isotope called deuterium, and you'll meet that in year 13 spectroscopy. So deuterium has 1 proton, 1 electron. Because the mass number is 2, it also has 1 neutron. There are 3 types of relative mass values that you should be aware of at A level, and you need to know precisely what they refer to. So relative atomic mass, fairly straightforward, A for atom, R is relative. We have relative molecular mass, and this specifically refers to covalent molecules, again R for relative. And for structures such as magnesium oxide and ionic lattice, we have relative formula mass, although the symbol MR may be used in some circumstances. So relative formula mass refers to giant structures, such as diamond, such as magnesium oxide, as I mentioned, ionic giant structures. Now, what these 3 values have in common is that they are without units. That's because they are compared to a standard atom. They're compared to the mass of the carbon-12 atom. So the carbon-12 atom is designated a relative mass of 12, which means 1 increment on that scale is 1/12 of the mass of the carbon-12 atom. So the R in these symbols refers to a comparison to the 1/12 of the mass of the carbon-12 atom. And that explains why it's just a multiple of how many times greater or smaller than an atom is compared to the carbon-12, so it doesn't have any units. One point to note is that these values are weighted means. Of course, you have just been discussing on previous slides the idea of isotopes. So which isotope should we take as being the true mass of a particular atom, or the true relative mass of a particular atom? Well, the answer is none. We need to take the mean of all the isotopic masses, but weighted for what is called abundance, which is a term we will explain in more detail in the next few slides. But so these relative atomic mass here is a weighted mean value compared to 1/12 of the mass of the carbon-12 atom. So how are these, or the data relating to the abundance of various isotopes achieved? Well, the answer is from an instrument which we obviously don't have in schools, called a mass spectrometer. It's very expensive. And from the information from mass spectrometry, we can determine the mass of any particular isotopes. How do we know that carbon has two isotopes, carbon-12 and carbon-14, from mass spectrometry. And how do we know the relative abundances? Again, from mass spectrometry. And from that, we can then determine the relative atomic masses in a way that I will show you in future. But let's start with just some barest outline of the way a mass spectrometer works. And this is not part of any potential examination, but a gaseous sample of an element and its atoms is entered into an ionization chamber. So the atoms are turned into ions, and those ions are always assumed to be 1+ only. By passing through an array of slits, a beam of ions is produced, which have a certain amount of energy or kinetic energy, and then they proceed to a detector. The ions are formed by the removal of an electron, obviously, and the detector is able, forming a 1 positive ion, the detector is able to count the ions on the basis of the electrical charge. So the detector will count the relative numbers of ions and the relative mass of each ion. So from the mass spectrometer, we get two pieces of information concerning the mass of a sample of a particular element's atoms. Firstly, the number of different ions, +1 ions, and the relative mass of those ions. So if we look at a model printout from a mass spectrometer, we will see that we've got on the y-axis abundance, which is essentially numbers of the particular type of ion, and we've got on the x-axis mass to charge. Well, the charge is assumed to be 1, so effectively this is a mass ratio on the x-axis. So for boron, we see that there are two signals, two peaks, one at mass 10 and one at mass 11. So that tells us boron has two isotopes, one of relative isotopic mass 10 and one of relative isotopic mass 11. We can also read from the y-axis the relative abundance. So 20% for mass 10, and 80 for mass 11. So this is the data that we get concerning the distribution of isotopic masses in a sample of boron. So this is our data that we get from the mass spectrometer, and from it, if you recall, we need to achieve a weighted mean. So to achieve that, we're going to do 20 times 10. So 20% of the boron has a mass of 10. So 20 times 10 plus 80%, so 80 items times 11. So we've got 20 plus 80 makes 100. So the numbers of items that we're sampling is 100. So to get the true average, we do, or the weighted average I should say, we get 20 times 10 plus 80 times 11 divided by 100. And that comes out as 10.8. So the relative atomic mass of boron, the weighted mean mass compared to 1/12 of the carbon-12 atom, is 10.8. So here's a problem. Calculate the relative atomic mass for rubidium. Here is the data, mass to charge, abundance. The abundances are written here for you. These are the isotopic masses in the wrong position, but those are the isotopic masses. Use that data to calculate the relative atomic mass for rubidium. Pause the lesson, come back when you have your answer and compare it to mine. Okay, so let's have a look at some of the working. So it's 72 times 85, 72 times 85, plus 28 times 87, 28 times 87. The numbers of items is 100, so divide by 100 gives you 85.56. Is that an appropriate number of significant figures? Well, the question asked you to solve to 3 significant figures. So 3 significant figures would be 85.6. So moving on to relative molecular mass, which is simply the sum of the relative atomic masses of the elements in the compound formula. So let's just do a couple of models. I'm sure you'll be familiar with this if you have done GCSE. So the relative molecular mass of carbon dioxide is 44. Where does that come from? Well, of course, we've got 1 carbon and 2 oxygens, so we take 12 as being the relative atomic mass of carbon and 16 for oxygen. 1 times 12 plus 2 times 16 is 44. Second model, the relative molecular mass of magnesium hydroxide. So interpreting this formula correctly, 1 magnesium but 2 oxygens, the 2 outside the bracket multiplies everything inside the bracket. So 2 oxygens and 2 hydrogens. Substitute in the relative atomic masses, comes to 58. So to reinforce the idea of relative molecular or relative formula mass, do a few problems. Pause the lesson, calculate the relative molecular mass of sulfuric acid, H2SO4, and all the other formulae, and come back to check your answers when you are ready. So here are a set of answers. The most problematical, which I'll just focus on, are the calcium nitrate and the hydrated copper sulfate. So the calcium nitrate, we've got 1 calcium, but we've got 2 times everything inside the bracket. So inside the bracket is 1 nitrogen and 3 oxygens, and multiply that all by 2 comes to 164.1. Now for the hydrated copper sulfate, straightforward, 1 copper, 1 sulfur, 4 oxygens, but this 5 multiplies water by 5. So 5 times the relative formula mass of water, which is 2 plus 16, comes to 249.5. So for my final slide, just the obvious statement that to consolidate you need to practice, you need to find problems from whatever source you have available to you, but those sources which have comprehensive answers are the best. So attempt the problems, check your answers. Move on when you are being consistently accurate and complete in your answers. Choose the next topic that you think for you is the one you need to focus on.